everyone. Welcome again to the Applied Topology online seminar. The speaker today is Christian Lehn, and he will tell us about limit theorems and topological data analysis.
Thank you very much. Thank you for the invitation. I'm very excited to be here. I mean, whatever this means in an online seminar, but I mean, to be here virtually or whatever. So the work that I'm going to speak about is limit theorems in topological data analysis, and it's a joint work with Sarah and Vlada Limic. So Sarah, you know, we just heard, and Vlada is a probabilist working in Strasbourg, and the three of us, we met at the Max Planck Institute in Leipzig, I think 1.5 years ago maybe. And this work is the outcome of our meetings. And what it is about is that it puts another layer of probability theory to topological data analysis, and it pursues some very, say, basic probabilistic questions in topological data analysis. So here is the outline of my talk. And I mean, as this is a seminar in applied algebraic topology, maybe some of you might get bored in, say, paragraph 1 or even the first 2 paragraphs. But let me point out that somehow our work is a result of a cooperation of different disciplines of mathematics, and I am definitely not an expert in persistent homology. So, I mean, this is somehow, if you wish, consider it as a warm-up for me. And of course, feel free to interrupt me and correct me whenever you think this might be necessary. So paragraph 1 and 2, they're more or less introduction and should be pretty standard, I think. The new contributions of our work is in paragraph 3 and 4, where we look at some limit theorems and calculate expectations of probabilistic objects in topological data analysis. And if time permits, at the end, I will explain some open problems and future directions. So, but let's start now with persistent homology. So it's the main tool of topological data analysis. The setup is this. You have a finite set of points in, say, R to the D. This is supposed to be the data in topological data analysis. And you could also replace R to the D by any metric space if you wish, but for simplicity, we'll stick to R to the D. And then the basic question you ask is, what can we say about the topology of this finite set of points? And if you look at this finite point cloud, which I depicted on this page, then I mean, it's pretty obvious that there is some geometry or topology inherent to that object. But if I ask this question so naively, then the answer is disappointing, and the topology is obviously trivial. It's a finite set of points, so it doesn't have interesting topology. So instead, what you do is you consider thickenings of this point cloud, and this reads like this. So for every non-negative real number, you consider PT. PT is the closed T neighborhood of the finite set P, and that's just the union of the closed T balls around all the points in this finite set P. And then we can study the topology of this, and this now will have more interesting topology depending on the parameter T that we choose. So let's have a look at this example once more. I mean, here you can see that you can count if you wish. So H0 of P, it will turn out to be Q to the 64 in this example. So for me, homology always means homology with rational coefficients. And H1 will be 0, so there are no closed loops in this point cloud. So that's P0, T equal to 0. And what happens if we increase the thickening? So if we increase the parameter t, then you see what happens. Now we have this green object over here. That's my sketch of what should have happened. And you see that now there are only 3 connected components. So this contributes 3 dimensions to the H0 of PT. There is this one, there's the small one, and there's the third one over here. And we just witnessed that there is a first homology emerging, which is generated by the cycle around this hole here. So this contributes to H1 of PT being equal to Q. So now what happens if you further increase the parameter from t to some bigger, say t prime, then we get this blue object here, and you see another change in topology. So the H0 is now Q. Everything has glued together. We only have one connected component, and the H1 of PT prime is now Q to the 3. So there are 3 independent cycles that generate the first homology, and these contribute 3 dimensions to the H1. And here is one of these cycles, gamma, a cycle around one of the 3 holes in this blue object. And the class of gamma is a class defines a class in the first homology of PT prime. So if you go on, then you see, I mean, from now on, the number of connected components won't change any longer. So you have T double prime in orange and this geometric object in orange that is the thickened point cloud. So H0 of PT double prime is still equal to Q, whereas H1 now has dropped. So why did it drop from 3 to 2? Well, that's of course because this cycle over here, the cycle gamma that we had before, well, it went around a hole, but the hole is not there any longer. So that means the cycle can be filled, and therefore it's homotopic to a constant path, and therefore the class in homology is equal to 0. It is still there, but now it is no longer different from 0. So we see what happens. Cycles are born and die in this process of thickening or point cloud. That's one thing that happens. And like formally, so if you have t prime greater or equal than t, you have an inclusion of pt into pt prime, and you get an induced map in homology between the hk of pt and the hk of pt prime just by the inclusion. But you have seen that this map need not be an inclusion. So it's an inclusion on the level of topological spaces, but obviously not necessarily on the level of homology. So let us formalize this structure in an algebraic notion. That is the notion of a persistence module. Persistence module V consists of the following thing. So first of all, we have a family of Q vector spaces indexed by the non-negative real numbers Vt, t greater or equal than 0, and moreover, we have a family of linear maps phi t, t prime, going from Vt to Vt prime whenever t prime is greater or equal than t. So this datum will form what is called a persistence module if the following properties are satisfied. So what we want is that if you map from t to t double prime, say, then this is the same as mapping from t to t prime and then from t prime to t double prime whenever this makes sense. And of course, if you map from t to t, then this should be the identity. So that's what we call a persistence module. And to single out well-behaved persistence modules, we introduced the notion of tameness. So a persistence module is called tame if the following things hold. So first of all of these vector spaces should be finite dimensional. And secondly, there are numbers t0 until tn in the non-negative reals, such that the following holds. Well, these n+1 numbers, they divide the non-negative reals into n intervals. I mean, the connected components of the complement of these finite set of points. And what we ask for is that this maps phi t prime, they should be isomorphisms whenever t and t prime are in the same interval, in the same of these n intervals. So the idea is that if you think back to our example from the finite point cloud, that some of these intervals, they or rather the ti, they mark the places where you have a change in the topology of that object. Okay, so that's a tame persistence module, and an example of that is persistent homology. So we have a subset of R to the D, and as I said, you could take, replace R to the D by any metric space. Then the degree K persistent homology of P is the case homologies of the thickenings of P. So we take the closed T neighborhood of P, we take the Kth homology of that, and we take the maps between the homology groups which are induced by the inclusion of the thickened sets P, T, Pt prime. And that is called PHK of P, that's called the persistent homology. So this is an example of a persistence module as I introduced it in the last slide. And so here is the main example for us. When you have a finite set in R to the D, then the persistent homology of this finite set is tame. And that's really easy to prove. So by the Nerv theorem, we know that the homotopy type of PT only depends on the non-emptiness of the intersections of the T-balls around finitely many points of this finite point set T. So, for every subset in P, you can ask whether this intersection I wrote down here is empty or is non-empty. And this is a finite number of yes and no questions, and therefore you have finitely many possibilities. And this is what in the end contributes to the tameness of this persistence module. Okay, and we build up the theory starting from finite sets. So if I want to be precise, I would like to use actually reduced homology instead of homology here everywhere. But you can also just ignore this comment, just for sake of correctness. Let me point this out. And now we can use this to construct a barcode. So at the beginning, for me, is somehow this theorem of Peter Gabriel from the 70s, which tells you that if you have a tame persistence module, then you'll find a finite number of intervals in the positive reals, in the non-negative reals, such that this persistence module is isomorphic to a direct sum of what is called interval modules. And let me quickly explain what an interval module is. So for an interval I in the non-negative reals, the persistence module Qi is defined as follows. I have to give you a vector space at the point T. So this will be Q if and only if T is contained in the interval and 0 otherwise. And well, for the maps, we do the only thing that is reasonable, namely we take the identity if both points are in the interval and the 0 map otherwise. So somehow this theorem tells you that all tame persistence modules are built of some very simple building blocks. And it's an interesting theorem. And the way you should think about this is that, I mean, you've seen in the picture that I've shown you before that sometimes there is sort of a loop that contributes a non-vanishing element in the homology of a given, say, PT, and it can be that somehow this loop dies in the homology at some point. So, I mean, of course, you can always pick a basis in the homology, but some of this theorem tells you how you pick coherently in the parameter t a set of generators. So if you have, the idea is that if you have such an interval module, then it corresponds to a homology class that is born at the starting point of the interval and that dies at the endpoint of that interval. So that's somehow the idea behind this theorem, I would say. And the interesting thing is that it's proven purely in algebraic way. It's a statement about representations of quivers. So conclusion of this discussion is that tame persistence modules, they're in one-to-one correspondence with multisets of intervals. So I1 to IM, what I mean by multiset is just a set where I remember that some of the intervals might show up with multiplicity. And this uniquely determines up to isomorphism the persistence module. And then on the right-hand side, the multiset of intervals, this is what's usually called a barcode. What you get if you draw this multiset of intervals, I mean, over the real line in a horizontal manner, then you get a barcode as it is, on products in the supermarket. Okay, so now let's introduce the space of barcodes. So for an interval in the non-negative reals, I mean, I can encode it by giving its initial point and its endpoint. Or equivalently, I can encode it by giving you its initial point and its length, which leads to a couple of two non-negative real numbers. We are precise, of course, somehow that's not really equivalent, but so an interval has an initial and an endpoint, but if I just give you 2 points, then you lose some information about the interval, namely whether the initial and the endpoint are included or not. But for this talk, I will just ignore this subtle difference. It doesn't play a big role anyway. So the space of barcodes is the following thing. I look at r greater or equal 0 to the 2, so think of it as an interval, and then I take the n-fold product of this, so think of it as n intervals, and then I take the disjoint union over all n, right? And then I have to mod out by an equivalence relation, namely the following. So think of, I mean, they should encode multisets of intervals. So obviously, a multiset is an unordered object. So I consider B and B prime equivalent. So I consider them equal. I declare them equivalent if they're equal up to permutation and deleting zero-length intervals. So for some technical reason, I like to include intervals of length 0. So x comma d is a point in r greater or equal 0 to the 2. But somehow I don't want to consider two barcodes different if they just differ by intervals of length 0. So this is what I call the TDA pipeline now, TDA topological data analysis. I start with a finite set in R to the D, and I associate to it its persistent homology. Then I decompose it by the theorem of Gabriel into a sum of interval modules. And then I associate to it this multiset of intervals and call it its barcode. And this is an element in the space of barcodes that I just defined. And well, if I talk of a space of barcodes, I should also talk about a metric, because for the moment it's just a set of barcodes. Recall that there's the so-called Hausdorff distance, which I can define whenever, say, A and B are, for example, compact subsets in a metric space. And I define the Hausdorff distance between the two of them to be the infimum over all non-negative epsilon, such that A is contained in B epsilon, so the closed epsilon neighborhood of B, and B is contained in A epsilon. Right? So now I'm going to define the bottleneck metric on this space of barcodes. So given two barcodes, which I represent by somehow intervals indexed by some index sets lambda and lambda prime in B primary barcodes, the bottleneck distance between B and B prime is given by the following. So I somehow have to match these index sets of B and B prime, and I do this I choose some bijection between lambda and lambda prime, and then I look at the Hausdorff distance dh of the interval with index lambda 0 and to the interval I prime indexed by phi of lambda 0, and then I take the maximum over all indices. So of course, this does not yet really make sense because, well, the index sets lambda and lambda prime, they're in general not bijective. I mean, the length of the barcode can be arbitrary. So what I should better do is the following. I choose just a subset of these index sets, and I identify subsets. And then I take the Hausdorff distance of the two intervals. And of course, then I should think what happens to the things that I'm not matching, and they enter. So I take here the Hausdorff distance between the intervals that I match, and for the things that I don't match in either lambda or lambda prime, I just take the length of the interval divided by 2. Well, and I take the maximum over all of this, and then at the end I take the minimum over all matching. So that is yeah, it was shocking to me, but you can make sense of it, and it's a very reasonable metric on this space of barcodes, and it gives it a topology. And then, of course, the first question that you should always ask if you see a metric space is it complete or not? And it turns out that this is a non-complete metric space, which is not that surprising, because you could, for example, add intervals that are smaller and smaller, and then you see that they will not really contribute to the metric. So it's easy to build Cauchy sequences that cannot converge, because they would converge to a collection of infinitely many intervals, and by construction there are only finitely many intervals.
Christian, could I interrupt with a question?
Sure, go ahead.
So in this maximum, you have a Hausdorff distance and then those lengths. For the Hausdorff distance, that's the Hausdorff distance just between two individual intervals. Is that right? So could I replace that Hausdorff distance just with a distance between like points in the plane?
Yes, definitely you can. I mean, well, it depends. I mean, I'm a geometer. If you're an algebraist, then you might like the formula better, and if you're a geometer, then you might like it better to compare intervals as geometric objects. But yeah,
right. I understand. Thanks. Yeah.
Okay. So we will from now on look at the bottleneck completion of this metric space, and that's of course a complete metric space, and we will use it to define barcodes. So to this end, we look at the following subsets of the power set of R to the D. Again, you could replace R to the D by an arbitrary metric space if you want. So f of r to the d is the set of finite subsets of r to the d. Maybe I should add non-empty, but well, finite subsets of r to the d, and k of r to the d is the set of compact subsets of r to the d. And of course, a finite set is compact, so you have this inclusion. And then there is a theorem of Cohen-Steiner, Edelsbrunn, and Haarer from 2007, which tells us that the barcode map, so that's the map which to a finite point set in R to the D associates the barcode, through this TDA pipeline that I showed you. So this gives you a map from f of R to the D. It has a metric, namely the Hausdorff metric, to the barcode space with the bottleneck metric. And what they prove is that this barcode map is one Lipschitz continuous. So Lipschitz continuous with a Lipschitz constant 1. So that's again in formulas what it means. And this can then be used. So corollary that you easily deduce is that in fact there is a unique continuous extension of this barcode map from finite subsets of R to the D to compact subsets. And the only thing is that it does not necessarily take values in the barcode space, but should rather take values in the completed barcode space. And this is just a simple application of so if you're Lipschitz continuous, then you're uniformly continuous, and then you can always extend to the completion, and finite sets are dense in compact sets, and so on. So that is actually not very difficult. And now we can define barcodes for arbitrary compact sets. That's what we're going to study now, namely from the point of view of probability theory. So here is the setup that we consider. We look at a sequence of IID random variables which are R to the D valued. So think of just RD valued, random points in random vectors in R to the D. And if you have such a collection of random points, then you can put them all in a set, and this will define for you call a random point cloud. And you could associate to this point cloud the persistent homology, and this is what you could call a random persistence module. So everything that we had in the deterministic world up to now can be given a layer of randomness, and then we study the probabilistic behavior of these objects, such as, for example, the random barcode, namely the barcode of this random persistence module. And the question that we ask ourselves is, what can we say about the limit of this random barcode of the set of n points Pn if the number of points n tends to infinity? And so, for example, can we calculate it? And if you look at the TDA pipeline, well, that's actually a pretty complicated thing. So it might be just impossible to explicitly calculate anything through this TDA pipeline. So somehow I think the philosophy that we have is that you can't really calculate it, so it's probably easier if you can guess it. So if you have an educated guess what it should be, what this limit should be, then you should be able to prove that it's indeed the limit. So calculating by guessing somehow. And let me make this a little more concrete. So if C denotes the support of the probability distribution, then the idea is that we should have a convergence of the barcode of the point cloud as n goes to infinity to the barcode of its of the support of its distribution. I haven't really said what this is, and well, in general, it is probably undefined. But I'll spell this out in a second. So just small reminder on what I mean by the support. So I have a probability measure P, say on R to the D, and then, for example, a back measure. Well, that's not a probability measure on R to the D. It's a measure. You can define the support, in fact, for any measure. So the point is the set of all points in R to the D, such that for every epsilon positive, the epsilon ball around X has strictly positive measure. And that's the support. And support of the distribution P. And here is what we prove. So we're in the setup as above. So we have these IID random variables RD valued, and we put Pn, the random point cloud, and call P its distribution. And then we suppose that the support of this distribution is compact. And then we can prove what we stated before. Namely, in this case, if n goes to infinity, the barcode of the point cloud converges to the barcode of this compact set, which is now defined by what I explained to you a couple of slides ago, almost surely. So this is an almost sure convergence result for random barcodes to the barcode, somehow, if you wish, of the limit of this point cloud. And here I displayed the same statement once more. Let me just comment for those like me who are not experts in probability theory either. So we say that a sequence of random variables xn converges to a random variable x almost surely if the probability of the event that we have convergence is equal to 1. So we have convergence on an event of probability 1. That's convergence almost surely. And there is another notion of convergence in probability theory, which is convergence in probability, which is slightly different statement. It tells you that if you look at, say, the distance of the member of your sequence to the limit, you look at the event where this distance is greater than a given epsilon, then for all epsilons, for all fixed epsilons, if I let n go to infinity, then this probability will go to 0. So these are the two important notions, or two of the important notions of convergence in probability theory. And almost sure convergence implies convergence in probability. So almost sure convergence is the strongest possible convergence statement that we have. So in the setup of the theorem, that's really a strong convergence result. Also because on the probability distribution, except for compactness of the support, we do not have any hypotheses. So for example, no hypothesis on regularity whatsoever. Let me remark that the converse in general is not true. So convergence in probability does not imply almost sure convergence. And we prove this theorem again somehow by this result of Cohen-Steiner, Edelsbrunn, and Hara by proving the following lemma. Namely, we prove that the point cloud converges almost surely to the support of the distribution in the Hausdorff metric. And then by the result I just mentioned about the Lipschitz continuity, you can deduce this theorem. And actually, it's a cute result, but what's even nicer is that the proof is actually very easy. So the proof of this lemma I'd like to sketch. So it works as follows. So if you have this point cloud converging to I mean, you want to show that it converges to C almost surely. With probability 1, you have that the point cloud is contained in the support. Well, that's somehow the definition of the support, right? Because you sample points from this support. So this implies that you can rewrite the Hausdorff metric of Pn and C just as the infimum of all non-negative epsilon, such that C is contained in B epsilon of Pn, because the other inclusion which will be there, this is automatic. And moreover, you have a monotonicity statement. So almost surely the Hausdorff distance decreases if you put in another point. I mean, that's also obvious because, I mean, just by definition, I mean, it can't increase. It can only decrease. And this is very useful because now we want to show something about almost sure convergence. But if you have almost sure convergence, and a monotonicity statement like this, then almost sure convergence is in fact equivalent to convergence in probability. So it suffices to show convergence in probability. And let me recall what this means. So here I have somehow the bad event. So that's the event where so omega is just some probability space that's floating around, and that is usually suppressed in probability theory, but that's always there in the background. And I look at the event of all omegas is that these finite point cloud and the support have a Hausdorff distance which is greater than some fixed gamma. That's a set, that's an event that depends on n, the number of points, and on gamma. And what we have to show in order to show convergence in probability, by definition, is that the probability of this set goes to 0 for all gamma if we let n go to infinity. And then the first thing is that you just slightly reformulate this set an gamma. So the Hausdorff distance being greater than gamma, that's equivalent to C not being contained in the closed gamma neighborhood of P. That's just by the remark that I made above, because Pn is already contained in C, therefore somehow the only thing that is missing is the other inclusion, and the distance being greater than gamma just means that you don't have inclusion. So now, if you don't have inclusion, well, then certainly that there's a point in C, call it Y, such that the gamma neighborhood of this point Y does not intersect Pn. So that is somehow the formulation that I would like to use to go on. So here is this last description of the set an gamma. I displayed it again here on the top of the page. And now we do the following. So we pick C1 to CL in the support C, finite set of points, such that C is contained in the gamma over 2 neighborhoods of the CI. This is, of course, always possible by compactness. And well, here is a picture for you. So this is the whole circle is C, and these spots, these are the points C1 to CL, and they are gamma over 2 dense. So if you have a Y as up there, then this Y will be in the gamma over 2 neighborhood of some point Ci. As a consequence, an gamma, this set, is contained in the union over I running from 1 to L of the following events. These are the events where the random point cloud Pn does not intersect B gamma over 2 of Ci, where Ci are these finitely many points that we chose. And this is just a triangle inequality. So suppose this set were non-empty, so suppose that there was Z inside, and so it's in the gamma over 2 ball around Ci, and we choose it to be in, so for one of the I, there is y lying in the gamma over 2 ball of Ci. Well, and this would imply that the distance of y to z, well, by the triangle inequality, that's smaller or equal than gamma. So in turn, z would be contained in the gamma neighborhood of y intersected Pn, which by assumption was empty. So such a z cannot exist, and therefore the set over here has to be empty as well. So we have this inclusion. So now we can easily estimate the probability, namely we estimate the probability of this A and gamma by estimating the probability of the sets here on the right hand side. Namely, the probability of the gamma over 2 neighborhood of Ci intersected Pn being empty, that is, first of all, it's the product of the gamma over 2 neighborhood of Ci not containing xj for all the j's. Then we go to the complement of this assertion, namely xj being contained, and that's why we have the 1 minus over here. Then we take product from j equal 1 to n, and this is this probability over there. So that's the estimate of the probability of one of the sets here on the right hand side. And because all of the xj are identically distributed, this xj here can be replaced by x1. So now I have the same expression to the n, right? So we deduce now that the probability of a n gamma is smaller or equal than L times 1 minus the probability that I've written here to the n. Okay? And now you just use the definition of the support. So Ci is contained in the support, and by definition this just means that the probability of this gamma over 2 ball is strictly positive. So if this probability is strictly positive, then 1 minus it is strictly smaller than 1. And if you take the nth power of it, then of course this will go to 0 if you let n go to infinity. So that's the complete proof, and it's a very nice result, I find, and for this the proof is really simple. Any questions so far? Okay.
Question. So this will hold also for Viator-Schrips complexes. You just apply the Chazal result for Viator-Schrips complexes instead of for check complexes. Is that right?
I think so. You have I think you have a different Lipschitz constant, right? It's I think it's Lipschitz constant is equal to 2, but well, maybe I should not be too bold. I would need to think about it, but I think it has a good chance of being true, because we can define the barcode of a compact set by the same method, and I'm not sure. I need to think about it, I think, because here the argument is pretty geometric, but I would guess that it's also true. I mean, we haven't looked at them, I must admit, but probably we should have.
Yeah. Well, you've decomposed your proof into this lemma, which is about the Hausdorff distances between sets, and then you use geometric stability. And I think there's an analogous geometric stability for Viator-Schrips, maybe with a different Lipschitz constant. But...
Yeah, probably.
Thanks.
Okay, thank you. Okay, so the next point I was going to speak about was expectation. So the goal is that we would like to calculate expected values for fixed sample size. And before I speak about the abstract results that we have, I should I would like to explain a guiding example that somehow led us to formulate the theorems that we've proven in the end. A very simple example, namely take the circle S1 the reals in R2 or C if you wish. So and then you take some random point cloud on this circle. So here is P5, meaning 5 points on this S1, which I painted here in green. And then there are some facts from. So the first one is somehow, I think that's, if you wish, that's sort of high school, non-trivial high school geometry, saying that if this finite point cloud is contained in a half circle, then for all times t, the Betty1 of the thickened point cloud will be equal to 0. And if P is not contained in this half circle, so any half circle, then you can show that the persistent homology in degree 1 of P will be an interval module starting at some point S and ending at 1 half open interval. So the Betty1 barcode of P will be S, 1 minus S, where S is the starting point and 1 minus S is the length of this interval. And well, so here is the setting is as before. We have the random n point set, and the question that we ask is, what's the expected value of this length, right? So the length Ln depends on n, where n is the number of points in P, and Ln is equal to 1 minus S. So that's a random quantity if the points are random, and what we want to do is calculate its expectation for a given n. So now the assumptions are a little stronger. We have n IID random variables, which are uniformly distributed on the circle. And then, well, I give you an example. So here is the expected value for L3. So the length of the barcode for 3 points. That's a very nice expression and a very nice exercise in integration theory. So what you get is 1 over 4 plus 9 over pi squared times the difference of the square root of 3 minus 2. Very nice expression, and so to get a feeling for it, it's very small, 0.005. So that means that if you just have 3 points, then the one cycle in homology will live only for a very, very short period of time. Well, and there is another, explicit result for Ln. It's not completely obvious that n equals 3 gives the formula above, but this is, I find, a nice formula for arbitrary n. We did not really manage to simplify it any further, but if you're looking for a numerical expression, then certainly every computer can give it to you for a fixed n very quickly. And this is so far the nicest formula that we could find. Uniform distribution, just to remind you, that's the volume of the set divided by the volume of S1, where the volume here just means the one-dimensional volume. Now the question is, how can we generalize this? So because, you see, if you want to talk about expected values, somehow you have to have numbers, or at least vectors. So here we are in the lucky situation that somehow the barcode of this point cloud was determined by a single number, namely its length. So that is not that's not always the case, of course, because you don't always have just one interval in your barcode. So, as I said, the problem is the barcode is not determined by a number in general, and instead what we do is we go to a more general setup where we consider continuous maps from the completed space of barcodes to some Banach space. So if you're not determined by a number, then at least you might be determined by a vector. So, for example, in Sarah's work about tropical coordinates on the space of persistence barcodes, you can find such maps which are not only continuous but which are embedding. So you really determine the barcode by a vector in some Banach space, which unfortunately in general will not be finite dimensional space any longer. But we have a little more general statement where we just look at maps to some Banach space, need not be embeddings. And then by general theory, if beta is a barcode valued random variable, then the expectation of the transform T of beta exists if the expectation of its norm exists. And this is always the case for barcodes of samples from compact sets. So this always makes sense to state it like this. And here I can maybe as a last thing I'll do, I can state the theorem that we have. So if you have a smooth compact submanifold of R to the D, and if you have IID uniformly distributed random variables on M, then you consider the point cloud, random point cloud Pn, you consider the Lipschitz continuous map to some Banach space. Then we have that for all epsilon sufficiently small, following holds, so that's an inequality for the expected value of the barcode of the random point cloud. So you see there are two things. That's the barcode of the random point cloud and the barcode of the manifold. The manifold in this case is also the support of the distribution. And now we go to the Banach space on both sides with T. The object on the left is still random, so we take the expected value. That's the quantity that we want to know. And we want to know it by somehow estimating how far it is from this deterministic quantity over here. And there is an explicit inequality which tells you that it is close to that. And my time is, I think, already up. So let me maybe just say that well, you can explain each of these terms on the right-hand side, and it helps you to bound the value you want to get by first choosing epsilon, and then once you've chosen epsilon, you have to let the number of points be sufficiently big in order to remain below a certain quantity. So this formula can be explained in detail, but I don't have times any longer, and I think I don't have times either for talking about open problems. So let me just stop by thanking you for your attention.
Okay, so questions. Thank you, Christian. Questions?
Can you tell us briefly about some of the open problems you're interested in?
Oh, of course, sure. Thanks for the question. So, here's a list. The list can be I think, continued very far. So first of all, we would like to understand distributions with non-compact support. And for example, there's also the question of including error terms. If you think in terms of data analysis, then what we did was somehow analysis for perfect data that lie on a prescribed manifold, but in practice it won't in general, and might fail to lie on this manifold, and it might in general with low probability lie far away. So it might be that we have error distributions with unbounded support. So it would be interesting to understand distribution with compact support. Then there are some somehow aesthetic questions. So can we prove a tameness result for manifolds, for example? We have defined a barcode for compact spaces, which in general need not be tame. Need not to lie in the barcode space, but rather in its completion. But maybe for manifolds it does. Compact manifolds, that would be a question which I'm interested in. And then also practical question would be, would be whether we can calculate this limit of this distribution somehow explicitly. I mean, of course, you have to make some assumptions on the distribution that you're looking at. But can we explicitly calculate the limit of these barcodes? That would be something that I would be very much interested in.
Thank you. Any other questions? Okay, so no questions in chat. Since I'm one of the co-authors, okay, Henry, please.
Could I ask you another question? In your example with on the circle, you're growing those balls. You're growing those balls in the plane as opposed to growing those balls in the circle? Is that right?
That is correct. That is correct. Yes.
Okay. If you're interested, you could also consider growing balls in the circle, and then you can get higher homology, it turns out. So if you're interested in computing expectation, like the nerve lemma no longer needs to apply when you can get these circular arcs that intersect. It's no longer a good cover. Anyways, if you're interested in computing expectations in that context,
so there's also Bubenik and Kim. I mean, they looked at that example in a circle already. So, I mean, like we looked at it slightly differently.
And what was the difference between how you did it and how Bubenik and Kim did it? Because I know that paper you're referring to.
Well, they, I mean, first of all, they take a different distance. So they take I think just the arc length, whereas we take the distance in R2.
I see. So they're using the arcs in the circle.
Right. Yeah.
But I don't remember so well. Do you, Sarah? I think they're more interested somehow in the H0 than in the H1 for some reason.
I think they're like also H1.
Okay.
Yeah.
Yeah, so in both your setting
that would be the inspiration for picking this particular example.
Right. In both your setting and their setting, you can get as much H0 as you want, and you can only get one H1 interval, right? What's interesting is that in their setting, you can also get H2 and H3 and H4, but I don't think it's been studied so much from the probabilistic side.
Oh, I see. I didn't notice that they have higher homology. Okay.
No,
they don't consider it in their paper,
right?
But
yeah, they just look at H1 and H0.
I see. Okay.
Yeah.
Thanks.
Okay, very good. Yeah, thank you so much, Henry, for the questions. And with that, I would ask everyone to unmute themselves so that we can clap for Christian. And thanks so much for joining us. The video will appear on YouTube, and we will see you next time. Bye.